Okay, everyone. Good morning, afternoon, evening, wherever you are. My name is Bruce Momjian. I am one of the Postgres core team members and an enterprise DB employee for 15 years. I am very happy to be speaking to you today about database hardware selection guidelines. Yesterday, I gave a well-received security talk about security in Postgres. This talk, along with several dozen other talks, is available at this website right here. So if you want to go to this link or use the QR code, it will take you to my website, which has over 20 talks, including video of me giving the talks. So again, you can kind of watch this talks and look at the slides at the same time. Wonderful, having a wonderful time here at Percona and enjoying the presentations. This is really, honestly, an ideal talk for Percona. It is related to open source database, particularly Postgres, but it's generic, meaning that it really applies to almost any database. And thirdly, it's about performance. So kind of combine open source database, performance, generic database talk. This is really kind of the sweet spot. I always enjoy the Percona conference, whether it's in person or online, and it's an honor to be speaking to you today. So we have about 30 minutes. Let's see what we're going to talk about today. This is kind of a goof slide. I sort of throw it out there. Every time I talk about performance, and frankly, whenever I sort of think about performance, I start to focus on these things, okay? And we see that a lot when people come to the Postgres community asking questions about, hey, I have a new server. What should I, here's the specs. Is it good? Is it not good? They always focus on CPU first, and then they talk about gigahertz, and, maybe it's a multi-core, multi-socket, and so forth. And they may talk about other aspects, but this is kind of what they lead off with. And that's okay if you're doing gaming or you're doing a lot of very fancy like image editing or video editing. These things are like super important, right? But for a database, not so much. And this is really kind of, I would say, the crux of one of the two things I want to talk about today, is that you're a lot of times when people talk about performance, they're almost thinking of it from a sort of gamer perspective, or I don't want to dismiss gaming. I have 4 children, so gaming is really important to them, but when we're speccing a database, these are probably not the things you're worried about. And I'm going to explain why. And I'm going to explain how you really should focus on what is important for a database. And that's really kind of a change in perception. Okay. And I think that's really what I want to get across. Because normally when you think of a server, the first thing you think of the CPU, second thing you think of is how much memory it has. And the I/O kind of comes in at the end, and it's usually related to how many gigabytes, how many terabytes, is it striped? These kind of generic I/O things may come in at the end. That's normally the way that people think of it. And I'm going to argue in this talk that you should think of it this way. As you can see, a little itty bitty database at the top, the CPU at the top, right? And then memory. And then I/O, because again, when people come to us talking about hardware config, they're typically talking CPU first, then memory, then I/O. I'm saying flip it over. Talk about I/O first, then talk about memory, and then talk about CPU. Now, there are a couple cases where CPU is important. I'm going to go over those, but don't ignore the other two, because the other two will really be the sweet spot in terms of where you want to spend your dollars and where you want to do your tuning. All right. Because I'm going to explain exactly why that is true. So why? What is it? Why am I giving you a pyramid that doesn't make any sense, that isn't normally the way you think about databases? There's probably a couple reasons. because the normal server workload, and my server's right over here to my left, the normal server workload is typically CPU constrained. We're talking about network overhead, text processing, virtual machines or containers, application servers, application code. All that stuff is very CPU intensive. So that's why most people, when they think of that triangle, are thinking of the CPU as this big thing at the top, and the IO is just something I need to throw my data somewhere. I need to put an executable somewhere. I need to put storage somewhere, but I don't really care how fast it is. It's just this. How big is it? Is normally I'm not usually worried about how fast it is. I'm worried about how big it is. Okay. And I will argue that while that might be true of generic servers running generic workloads, that is not true of databases. Why is that not true of databases? Because databases have unique requirements. They stress a server in a different way than almost any other application I can think of. And if you're going to get good performance, you have to change your mindset to think the way the database needs. Think about the database needs. Don't think of how fast it can run, a computer game. Think how fast it can run the database, because that's what you're specing the server for, right? So, for example, large sequential scans of large tables. Databases do this all the time, whether they're doing a select, whether they're creating an index, whether they're doing a big join. It happens all the time. How many other applications do this? Not a whole lot. Index scans, which cause a lot of random I/O. Again, another thing that you just don't see a lot in normal workloads, but databases do these things all the time. Okay. So you can see even from these first two, the concept of I/O is becoming very important, because these are part of the requirements for, this is the part of the requirements for doing these kind of operations. Okay. Unpredictable query requirements. Databases are doing that all the time too. They're just running a query here and then a data warehouse there, and then, I'm going to update a whole bunch of stuff here, and somebody ordered a bunch of there. I'm going to do fraud detection. All these things are happening all the time, at night, in the day, when people are there, when people aren't there. Jobs running, reports running. These are this is just plain regular workload for a database. Not really true of many other applications out there. And the key point is that most of these do not require a large amount of CPU resources. Yes, you need a CPU. Yes, they need to be sized properly, but that is not where you want to start worrying about performance and worrying about where to invest your money. You have to think of that triangle with the I/O at the bottom being very wide, and then the CPU very small at the top. This slide, which actually appears in 2 or 3 of my other presentations, is sort of a snapshot of how Postgres works. This is very similar to how other databases work as well. So I'm just going to kind of go through this to try to break down exactly why what the kind of pressure, what the needs are on your database server. Okay, so at the top in purple, we have a bunch of Postgres backends, in this case 3 of them, but again, it could be hundreds. Over here on the left, we have what we call a shared buffer cache. So this is a shared part of memory that effectively is where all the reads and writes happen for your applications. So in 8K segments, you're reading and writing a whole bunch of pages from the file system. Okay, if a backend in purple here wants some data, it's going to check the shared buffer cache. If it's in the shared buffer cache, it can operate on it right away. If it is in the shared buffer cache, it's going to need to make a request to the kernel. So the kernel there in green is going to be fielding the request for a page that is not in the shared buffer cache. If it's in the kernel cache, that will be returned and copied directly into the shared buffer cache. If it isn't in the shared buffer cache, it's going to have to go down to the disks or the storage. Okay. And the storage is going to then back up to the kernel back up to the shared buffer cache, and then the session starts running again. Okay, so that's the kind of flow that you typically have, that you can very easily stall your sessions if shared memory isn't big enough, if your IO system's too slow or it's overwhelmed. All of a sudden you get really bad performance. As you can see here, I haven't mentioned CPU at all, because in most cases, applications are going to be either IO bound or memory bound before they're CPU bound. There's another aspect of database that's pretty important that I have to mention, and that is the durability requirement. As you may know, for relational databases, they have this requirement of durability, which means that you have to store all of the changes in a durable way before you report the transaction as committed. Okay, and Postgres is no exception there. So over here in blue, we have the durability part of Postgres. Every time a session in purple has to modify a shared buffer, it will also write the change to something called the write ahead log. And before you actually mark the transaction as committed, you have to write it to the kernel, and then you have to issue an fsync for the kernel to write it to the storage. Now, the storage I'm showing is one big block, but it can be broken down. I'll show you in a minute. But effectively, every commit has to wait for that durability to happen. So no matter how fast your CPUs are, even no matter how much memory you have, you're still going to have this throttling going on, where you're waiting for the shared buffers to be written. Okay, I'm sorry, you're waiting for the write ahead log to be written, and that is a critical bottleneck typically with databases. Okay, so let's take this slide and break it up into some parts, start to put some names on some of the components, and start to look at how we might speed this up. Okay, so here's the same slide, except I've taken the part below the kernel, right? I've taken the part below the kernel cache here, and I've actually broken it up into pieces. Okay, so the most traditional way to speed up a server like this is to add something called a host bus adapter or a RAID card that has some type of cache on it. Okay, and therefore the cache can respond really quickly, and depending on whether that's durable or not, it can actually improve your performance quite dramatically. And we also talk about the cache, whether it's write back or write through. A write back cache is hopefully durable. It doesn't wait for lower layers to get the data. Write through cache requires the data to go through. Then there's also cache on the disk typically, and then there's the magnetic disk underneath it. Again, this is the sort of old school way that you would set up your IO stack. But fortunately, and in the past 25 years or so, the idea of having a battery on the HBA has become very popular. And when that happens, you effectively do not need to wait for the data to get down to the lower levels of storage, because the battery is going to make it durable. And as soon as the battery makes it durable, your job is done. Okay, you don't have to wait anymore for data to get any farther down. As soon as it gets into the HBA, HBA says you're good, replies acknowledge right away, and the system can acknowledge the transaction and continue to the next transaction. So you can see this is a game changer in terms of having to wait. Either you're going to have to wait for the data to get through the HBA to the disk cache and then to the disk, and the disk going around 15,000 RPM. You got to wait for the head to come around, all these, crazy, terrible, slow things that happen. But you're kind of amazed at how many people would just have it that way, because they don't realize when they're in a database workload how important that write acknowledgement is to durable storage. Okay. But as I said before, this is sort of older school. Newer methods typically will use something called like flash or NAND storage. We call these SSDs, and effectively they would have a durability disk cache. In fact, it's not actually a cache; it's the staging area. So you really can't turn it off very easily. In fact, you shouldn't if it doesn't have a battery. But if it has a battery, then it can just go in there, acknowledges right away. And this is the big difference between enterprise SSDs and consumer SSDs. Consumer SSDs typically don't have a battery. Enterprise SSDs typically do. And again, this is night and day in terms of performance. If you have a battery on your HBA, you probably don't need to worry about this layer. But if you don't have a battery on your HBA, then this getting a battery on your SSD is critical. In fact, if you don't have it, not only will it be slow, but you effectively could corrupt your database. And when SSDs came out years and years ago, we did see that quite a bit where people were using non-battery backed SSDs caching. The cache is always right back for reasons of the way NANDs work, and effectively they lose power and they corrupt your database. The final way that you see, and this again, there's a whole range of technologies out here that do this DRAM storage. There's a whole bunch of names for them now, but effectively they're DRAM. They're not SSDs, they're not flash, they're not NAND. They're literally DRAM chips with a battery. They always have a battery because they're DRAM. If the battery left, then you lose your data, and nobody buys the data. Nobody buys a drive that when you turn it off, it erases, right? So the good news is all of these have batteries, and effectively you have the ability here to you almost don't even need the battery on the HBA anymore, because again you're just going to flush everything down to the DRAM. DRAM has a battery. You're all done very fast. In fact, I've had arguments in the Postgres community of whether the battery backed HBA is really a thing anymore. Do we really need that anymore if we have things like SSDs and DRAM based, NAND based and DRAM based SSDs, which effectively are so fast that the HBA. I actually have a server that does not have a battery on the HBA. In fact, I don't even have an HBA because I didn't need one, and I already had an SSD with a battery on it. So, why add that extra complexity and that extra option of failure if I don't need it? So I would argue, and I've got some blog entries about this, and there's a whole performance section of my blog entry talks about effectively, is that whole battery backed HBA really something we need to worry about anymore? Or is it just something that was part of the magnetic disk era that really doesn't apply? Again, this term of write back and write through, I just wanted to kind of explain it. Write back means that you acknowledge right away. Write through means it goes down to lower layers. So when you're talking about those terms, just kind of be clear there. Okay. Again, there are multiple caching layers typically in a server. There's an HBA. There may be an HBA which has a cache, which may or may not have a BBU or a battery. There's going to be cache on the storage, whether it's a magnetic disk or an SSD that's NAND based, or an SSD that's DRAM based. There's typically going to be a cache there, and you need to understand whether that cache is battery backed or not. I'm going to show you some pictures in a minute to kind of figure it out, but effectively you have to now do your research, because most consumer level things are not worried about adding batteries there. For DRAM they have to, but for NAND they don't. And I would strongly recommend against using those for database workloads for that reason. That's why normally enterprise or SaaS based devices typically are better, or it just makes sure when you're buying something, because again, if you're speccing for a database, there's not a lot of people who are going to realize what your database is going to be doing that's different than what everyone else is doing. And it's your responsibility to know that and to pick hardware that matches those requirements. Okay. Again, you can have caching on the HBA. You can effectively have a battery on that or not. If you're choosing magnetic disk, which there's not a whole lot of anymore, but if you're using large amounts of data, people are still using magnetic disk. You can get away with magnetic disk, particularly if you have an HBA with a battery, because again, you're not waiting for typically the data to get durable. You can durably write really quickly. More spindles is better than a few larger spindles, obviously for parallelism. RAID 5 and 6 typically you do not use for databases. I'm not saying they're completely wrong, but the write requirements for RAID 5 and 6 typically require writes to multiple drives to be synchronized, and that's typically too slow for databases, because databases are going to wait for those writes to happen in a lot of cases. RAID 10, very, very popular with databases. So if you're thinking of RAID 10 is really where you want to go with any kind of database you're concerned about performance. Another thing that I think is super important for databases, make sure you have smart reporting enabled. Smart reporting effectively is sort of a warning, gives you warning signs about the drives and storage devices. There is a smart API that allows the server, I think it's smart CTL daemon, that actually probes the hardware every couple hours and asks for error reporting information. If it finds any, it alerts the administrators. So if you're running a database and you don't have smart enabled, I think that's a mistake, because the sooner you can get reports about bad hardware, the better. Again, in terms of SAS versus SCSI, just don't try and save a lot of money on drives. It'd be the simplest way. Reliability, error reporting, a drive that's designed to work 24 hours a day, one that's designed to have vibration from other drives in the cabinet, one that's designed to handle heat. Those are very important. Now, I only have anecdotal advice on that, but effectively, I have a tendency to purchase more of the enterprise drives for my home. And, maybe I've replaced 2 drives in the past 15, 20 years. I have a friend who buys the cheapest drives possible. He's up in New York City, and he says every 18 months he's replacing the drive. And I'm like, okay, like if you enjoy doing that, but I'd rather spend more money and not do it. So that's kind of the way I've sort of looked at it. But it's very hard. It's very hard to identify what is a quality drive, when is the extra money worth it. You kind of have to figure it out. It's not, they don't make it super simple. SSDs, certainly very important. 2 types of SSDs, as I said before. There's NAND or flash-based SSDs, which may not have a battery. And then there's DRAM ones, which certainly do have a battery, because DRAM would go away. There is a staging area. It's not technically a cache, although it acts as a cache. It is almost required to be write back. So you can't write through an SSD cache. If you do, you'll burn out your SSD real fast, especially if it's NAND. So again, that having a battery on that staging area is pretty critical. Again, if you're using Postgres, the SSD and pretty much all databases, SSDs are ideal for the write-ahead log, because they acknowledge writes very quickly, and that's exactly what happens when you're committing transaction. You're writing that write-ahead log to disk. You want to acknowledge that quickly. SSDs can do that. And of course, SSDs have much better random I/O performance than magnetic disk. Specific to Postgres, if you are using SSD, you can set the random page cost to 1.1. In fact, you can use a mix of SSDs and magnetic in Postgres. And for each table space, you can set a different random page cost. So it kind of allows you to mix slow random cost and fast random cost devices on the same machine, and tell the optimizer which ones have those behaviors. Another issue with SSDs specific to Postgres is effective I/O concurrency. SSDs are obviously very good at multiple concurrent I/O requests, so you can kick it up to like 256 and allow the server to kind of query a whole bunch of stuff at once and get much better performance that way. For file systems, I normally recommend XFS or ext4 over ext3. There's been some performance measurements on that. ZFS, everyone loves the snapshot feature, but it's not. It's quite a bit. It's somewhat slower, and it can be buggy, particularly because there's so many options of how you configure ZFS. So I'm not saying don't use ZFS, but I am saying you'll take a small performance hit, and be careful how you configure it, because some of the settings will remove the durability of the database. So just don't do that kind of blindly. XFS and ext4 pretty much can't break them. They run fine. The performance numbers are pretty much the same on the two. You can reduce file system logging, particularly on the write-ahead log directory. And you can remove A-time if you think that's important, although more modern Linuxes are better at that. I have been talking about the concept of a battery-backed unit. That's effectively this extra amount of sort of battery that's sitting on either the HBA or the storage. Make sure if you buy something and you think it has an BBU, that it actually does. Sometimes for HBAs, the BBU has a limited amount of time it can run, so be careful of that. They have actual batteries on it. Make sure you monitor it for failure and so forth. That's still an issue on HBAs. Here's an old HBA card. You can see on the top right here, there's a battery. I'm going to zoom in on it. Actually, you can't, but right there, there's a battery right there. That's the battery right there. This is a SSD, and you can see the batteries right here on this right-hand side here. These are all batteries. Okay. So again, that is an enterprise SSD. It has battery. Shared storage. Shared storage is great for management. Just keep in mind that it is shared. So you are going to get, it is a shared resource. Databases are going to wait for IO completion. So potentially it means you might have to wait for some IO to complete. So just be aware of that. There's nothing wrong with it, but you can use SAN, you can use NAS. It pretty much runs just fine. But again, it is a shared storage. And again, be careful what options you use, because the durability requirements have got to be met for those storages. Okay, we spent all the time talking about storage. Let's finish up talking about RAM. RAM, effectively, the more the better. Not much more I can say about that. Ideally, if you had 5 minutes of your working set in RAM, that would be fantastic. The more RAM, of course, the more possibilities of errors. For a database server, I recommend ECC RAM. It is more expensive, but I do think it's worth it. Detects errors, corrects errors, reports faulty memory. You may think everything's fine, but even cosmic rays can cause memory errors. They did an experiment. They took a server at sea level. They put another one on a mountain for like a month, and they could actually see a difference in the number of RAM errors between the two. Finally, CPU, that last thing I was going to talk about. Parallel query can use a lot of CPU. So if you're doing a lot of parallel query operations, again, CPU can be helpful. If you're using a lot of server-side functions, CPU can be important. And of course, if all of the data fits in RAM and you have a read-only workload, then effectively you're not using a whole lot of I/O. And in those cases also, RAM can be super important. So in conclusion, these are 4 cars. They all have 4 wheels. They all have a steering wheel, but they're completely different cars, right? And that's the way hardware is. It might all be SCSI. They may all be SSDs. They may all be made by Intel. They might all, have a similar appearance or not. But in fact, they all do different things. So just be aware of that when you're selecting hardware. And that is all I have to say for today. Again, that's the slide you want to remember. I do not believe I have any time for questions, so I will answer the questions in the chat, which I think is the way to go. Hopefully you'll be able to, if you're going to go to another session, I'll be typing them in the chat if you have any questions, so you can come back and see my replies. So thank you very much. Appreciate it.